so last class we finished off with this data set, and we were talking about how would you fit this data set. And so the issue is, and this is always the issue with linear regression, is that linear regression is very heavily dependent on which variables you put in it. I mean, maybe that's not so surprising when you say it like that, but a lot of people sort of have this impression that the coefficients sort of are some real life thing, and that the coefficients really are part of your model. They depend on what you have put in or not. That's what we were talking about last time. And we had this data set where within each individual group, the trend is down, like an increasing x1 within each group is decreasing the y value. But the overall trend, if you just ask x1 versus y, the overall trend is positive because increasing x1 makes it more likely you're in the big group than the small group. So this is where we're going to pick up off. And today we're going to also have some sort of practical tips for your project and things like that. So that will be coming up. Any questions or comments before we get started? Okay, so last class I said some things about this. This is sometimes called Simpson's paradox. You have the x1 and the y. This is actually a data set I made up where there is not only an x1 and a y, but there is an x1 and an x2 as well. So if we plot all of them together, this is what it looks like. This is what the actual data set looks like. And there's a very nice command called SNS, which stands for, what does SNS stand for? I don't even remember. What is SNS? SNS is like seaborn something. Where is SNS? Let's see if we can find it. Okay. Well, now I've lost track of it. Oh yeah, here it is, seaborn. Yeah, so seaborn is another one of these things like pandas and so on that has some nice data visualization tools in Python. And this one is called a pair plot, where we have all the possible combinations of the variables x1, x2, and y plotted all together. And on the diagonals, these are the histograms. So x1 with itself, x1 is this really funny data set where there's some on the outside, there's some in the middle, and there's some on the outside again. x2 with itself, x2 is a really, really bimodal data set. This is where we see the two groups. There's a group on the left, there's a group on the right. Y is kind of spread out all over the place. So that already gives us a good sense of what's going on here, starting to think about these things. And the thing we saw before of having two different groups, maybe that's related to our x2. And indeed, if you look at x2 versus y, you see the low x2 values have low y's and the high x2 values have high y's. So the x2 was kind of controlling this group action that we saw before. So in this group over here, that was x1 versus y, and the secret group identity is actually being controlled by x2. That's what it looks like to us. And so based on this, I might make some different things. And so one thing you might do is you might do, this was the plot of the regression of x1 versus y, that nice linear fit. And the thing is, this is giving me an RMSE of just about 2.93. And you might say, okay, we have x2, let's just use x2. So let's do a linear fit with x1, x2, and y, right? And that is this one. And you can see this is actually quite a lot better. So the RMSE went down from right around 3 to down to 1.3. So a huge improvement. And this is like fitting the thing a lot better. And I think a lot of people would sort of stop there. And they would say, okay, we got x1, x2, and y. And this is like about as good as we can do. But the thing I mentioned last time is that actually it looks like it doesn't actually matter if you have a large x2 value or not. It really looks like the x1 is the thing that matters. And it's in these two groups. So we want groups based on x1, x2, and y. And so I made a new variable called group, and this is the one I was talking about last time. And it is just saying, look, is your x2 value larger than 0.5 or smaller than 0.5? And so this is the pandas way of extracting columns. If you're using a different sort of framework, you'll have a different thing. But sort of in Python, you do square brackets to say I'm accessing something. And I said, let's make a new thing called the group, and that's just whether or not x2 is bigger than 0.5. So if it's bigger than 0.5, you'll have a 1 here. If it's smaller, you'll have a 0. Or maybe you'll have true and false. True and false are kind of like 1 and 0 in Python. And so what I'm really doing is sort of I was inspired by this plot, right? So these plots with x2, they were really making me think, hey, it looks like there's two separate groups, and that's why I should do x2 less than 0.5, x2 bigger than 0.5. You might have the same kind of thing in your housing. Well, we can talk about that in a second. But if you do that, and then you do the regression, does anyone have, so now I have this group, and now I'm doing, instead of doing x1, x2, I have x1 group. And this has an even better error. So the training error, I'm trying to reveal the training error without revealing the plot. The training RMSE is only 0.94. So it went down from 3 to about 1.3 to about 0.9, which is a lot better. Does anyone have a guess of what it will look like? So I have group. This was x1 versus x2. The orange dots are the data, and the blue dots are my guess for the data. So like this over here, this orange dot is what we're trying to predict, and our prediction was this blue dot. So it's not perfect, but it's pretty good, and you can kind of see the spread. We kind of have a spread out thing and a spread out thing, and they're not great. What will it look like in this new plot where I'm doing x1 and the group? So I'm using x1 and the group as the input, and I'm doing a regression of x1 group versus y. What will that look like? Let's write down the equation. So I have this kind of stuff. This is the kind of thing I was talking about last class. Okay, let's see if we can find the note from last class. Okay, yes. Okay, very good. So this is the kind of picture we had. So and this is exactly the formula that I need. Y is beta hat 1 times x1 plus beta g times the g. And actually, there's also another term that is in there by default, which is beta hat 0, the constant. So what will this look like? Looks like what? So and here's a plot of x1 versus y. This is actually a y hat, I guess, our estimated value. What will it look like? Anyone have a guess or want to describe it? What does this equation look like? And maybe I'll remind you, g is either 0 or 1. 0 in group 0, 1 in group 1. Yeah?
Beta G change the intercept.
Beta G changes the intercept. I think that is true. Can you say more? Yeah, what do you mean by it changes? Because to me, this one is the intercept. I think saying it changes the intercept, I 100% understand what you're saying, but can you explain it in more words for people who don't?
There's a shift between the lines. So.
That's a nice way to say it. There's a shift between lines. So I think if G is either 0 or 1, then what is y hat? Well, it depends on what G is. And so you could write it like this. Y equals, you could say it's either beta hat 1 x1 plus beta hat 0 in group 0, right? Because if you're in group 0, then G equals 0. You plug in G equals 0 in the formula, and it just goes away. And then if G is 1, you have an extra term, plus beta hat 1 plus beta hat G in group 1, right? So what will it look like? It's two lines, but they have different intercepts. One of them, the slope is beta hat 0. The other one is beta hat 0 plus beta hat G. I wrote a 1 by accident, but it should be a 0. Okay. So you can sort of think about it, because G is either 0 or 1, this term, beta hat G, is either there or not, and therefore you can have it this way. Okay, so what will that look like? Well, there's two lines. The two lines actually must have the same slope. The only thing that is different is their offsets, their intercepts. So one of them is like this. So this is slope beta hat 1, and then the offset here, we'll say, is beta hat 0. And then there's another one in the other group where it's beta hat 0, and you add on an extra beta hat G. So beta hat G is the difference, and then this whole length will be beta hat 0 plus beta hat G. And then you'll have this other line that looks like this. So this is the other. So this is in group 1, and this is in group 0. So the whole model has three numbers it can play with. It can move both lines up and down together by changing beta hat 0. It can move the lines apart by changing beta hat G, and it can change the slope of the lines together by changing beta hat 1. And the model will find the one that minimizes the sum of squares, that does the least squares thing. So that's what it'll look like. And let's check and see if it worked in the code. And indeed, it looks like that. So it's a very nice thing. These two lines, depending on what group you're in. And it happens that because we were able to identify the group variable, either in or out, very accurately, we get a really nice, accurate thing here. Of course, this is a synthetic data set I made up to illustrate this lesson. In real life, it'll always be more messy than this. There'll be things that are mislabeled and so on and so on. We'll talk about some of those things in a little bit. But any questions or comments about this example, finishing up from last time? Okay, so what is the moral of the story? I guess the moral of the story, I guess there's two morals. One, there's at least two morals. One moral is, no, when you have things that are either there or not, you can think about them as either including a term or not including a term. That's a very useful way to think about things. And then the second moral is that when you include things, the right way, you can improve the error by a lot. So if you sort of do things the wrong way, you got a really high error, right? And you can kind of see that this is not accurately capturing what's going on. You could also plot what are called the residuals, and you would see that, look, it's always an overestimate over here, and it's always an underestimate over here. That's a sign that there's some more information you could extract. So this is kind of like not good, and you can see that it's not good. If you just do the very simple thing, if you have x1 and x2, then you get better. But you can do even better if you can sort of identify the true thing. And the true thing in this case was there were two groups. That's a very useful thing to see, and then you can do a lot better. You might say, let's take this moral. We figured out the moral. You add more things, you figure out the patterns, it gets even better. So here's the question for you. Let's keep going. So here's a new idea. So before I added this variable called group, and now I have a new variable called W. And W is going to be some specific part of the thing. And by adding in W, I can get a third line. So I can go over here, and I can have, maybe I'll split group 0 into two groups. There'll be like a piece over here and a piece over there or something. Okay, to keep it simple, let's just do a third slope. Let's do a group 0B. Group 0B. I'll further subdivide group 0 into group 0A and group 0B, and I'll have two splits. I'll split it up into two different lines. So let's say that's what this variable means. I just picked 0.1 and 0.2. I ran it. Could have been something else. And I ran this, and actually I got a better fit. The number went down even more. So where did the number go? Okay, we have to find, this is the hardest part, is finding the number. Okay, here it is. So before the training RMSE was 0.94, you could convert this into an R² value. The R² value tells you the ratio of the training RMSE to what it would be if it was a pure, straight, flat line. So that's it's a ratio of like how much better you're doing than the constant guess. So that's a useful thing. And let's say the R² value went up, which is actually, if you do it, it will actually go up if you do the right thing. So that's not some kind of lie. The R² value really does go up. But there's an issue. If you do this, you're going to run into an issue. And I want you to identify what that issue is. I'm going to open this up and give you a minute to try to tell me what is the issue with doing what I just said. It's a good time for questions or comments as well, if anyone has one about what is the setup or what we're doing here. Okay. Okay, one more minute to tell me what is the issue with doing this. Okay, last couple seconds, get in your final thing. Maybe it says, I don't know. That would be fine. What is the issue with adding this in? Okay, and again, we just saw the moral of the thing I just told you is that sometimes this works. But what's the problem with just adding another one? Let's see what people said. Okay, some people don't know, which is great. Some people wrote overfitting, very nice one-word answer. Let's see what other things people wrote. Dependence on a new variable. So dependence on a new variable on its own could be good or could be bad. So this on it, I don't know if this is an issue. This could be a good thing. And we just saw that sometimes it's quite good. So dependence on the group variable, that was great. That worked really well. But what else is there? Someone else wrote overfitting, cost. The thing is, linear regression is like the super fastest model. If you're doing anything with linear regression, the cost will usually be okay. So this is totally fine adding a variable. Maybe overfit. It could cause overfitting. The interpretation gets harder. Yeah, this is true. The more weird stuff you add in, the harder it is to interpret. I will say, in this course, we're usually interested in predicting accurately, and we're not as interested in interpretation. So if we're doing like stats and trying to like really interpret things and trying to give advice to like medical doctors, then the interpretation is really important. If you're a data scientist, often you just want to get the most accurate prediction, and the interpretation is secondary. So the interpretations get harder the more things you add, but on its own, that's not necessarily an issue. Okay, but overfitting is the overwhelming big thing. Did the overfitting move to the bottom? And that is also what I said. So if you wrote overfitting, that is what I would call the correct one-word answer. Of course, if you wrote it could cause overfitting, that's also correct. This could cause overfitting. And how would you know it causes overfitting? I even said the R² value got better, that things improved. And so this is a danger of the kind of notebook I was just looking at, which I have lost yet again. Okay, here it is. One dangerous thing I was doing. Can anyone see the danger in this line? There's one part of it that is dangerous. What is the danger? So I was trying things, and I was like, how good am I doing? Let's look at this number. Yeah.
The word training?
The word training, yes. This is a very dangerous word. So this number, if it goes down, it could mean two things. It could mean things are improving, or it could mean that I'm overfitting. And if you only say training, you will never know which it is. Of course, you sort of, as a first check, a sanity check, you can kind of play around with the stuff and see. But like at the end of the day, you want the actual, what would it be in real life with new data? That's like the test data set or the true error. And so the training RMSE here is some kind of proxy for what we want. And because of this overfitting phenomenon, it's not a good one sometimes. So I really should be doing the test RMSE. And I didn't do that here because I was lazy, and that's really bad. And you would see that if you start to add more variables, it doesn't generalize, even though the groups really are there, and they do generalize. So you have to kind of know how to test for overfitting so you don't add in too many variables. You want to add in the right number of variables and the right patterns that really are there that generalize to the full thing, and you don't want to add in stuff that doesn't exist. So sometimes you'll see ghosts that look like they're in your data set, and your training RMSE will go down because you're fitting these ghosts. Like maybe you'll say, oh, this number is really low. Let's go down and get that one. But that wouldn't generalize well, and that would be bad. Can anyone tell me what's even more dangerous than the word training here? There's one thing that almost everybody does that's even more dangerous than putting training RMSE. This one is very commonly done also by ChatGPT. What could you write instead of training? That would be even worse, like way worse than what I wrote. This is bad, and then like the next thing is like negative infinity, like horrible, like truly will screw you up for the rest of your life. Bad. The thing that people write is they write nothing. They write just RMSE. And then they're like, oh, the RMSE is going down, and then they work on it for a few hours, and they like go have lunch, and they come back, and then they're working. They're like, the RMSE is going down. Things are good. RMSE, it's good. If you forget to write the word training, then not only will you screw things up in the way that I said, you won't know what the problem is. So it's really important every time you have some kind of RMSE, I would blacklist just RMSE on its own. Always say what kind, training or test or true or whatever, or like I did it with cross-validation, whatever, something. There should always be an adjective in front of RMSE so you don't mix it up. If you just write RMSE and you forget which one it is, you can get into a lot of misunderstanding and a lot of trouble. Okay, great. Questions or comments about any of that? Okay, that was sort of the wrap up of the previous class. Now we're going to start the next thing. And in this class, we're kind of going over the practical tips for taking everything we've done with linear regression and how would you actually do it on your project. And a lot of this, I will say, I'm not doing a lot of details in class on like the actual detailed coding, so I'm giving you these coding things, and you can look over them and sort of use these as a starting point and copy them. But there's also, I will remind you, the whole class is sort of based on these videos that go with the textbook, and they have lab videos there. So these videos called .py. This means it's a Python lab, and in this video they go over it and they tell you what the individual commands do, and they sort of do things little by little, and there's code you can copy. And I highly encourage you, if you want to go through this, they're using the actual Jupyter Notebook environment, but you can do it all in Google Colab, which I've been using. And this is a nice way if you're not familiar with the stuff, like watch this video, pause it, and then type in whatever they typed in and run it and have it go. So some people will be very familiar with the Python, and some people won't be. And I also don't want to prescribe a specific way to do it, because things change all the time, so do whatever is good for you. So like they're using this sm.ols, which I also used here. I'll have some examples with scikit-learn as well, which is also very good. So you should absolutely, if you've never seen this stuff, don't feel like bad or like you're missing something. Like just go watch the videos and start to make your own notebook. You can pull in examples, and we'll have a couple more example notebooks today as well. Okay, so that is the kind of programming stuff, and we're going to see some of the like math and thinking stuff coming up. The next question is 3 quick little true falses about trying to use this stuff in practice. So true or false, true or false, true or false, and I will let you guys try these true or falses. Okay. Let's do. Okay, time's up. Let's see the true false questions. And so yeah, these questions were sort of made to go at the beginning of a class, and they actually went after a little bit of a warm-up from last class, so we'll see how that affected people's submissions. First one, 22 out of 24 people said false. In a large data set, it is always better to use more variables. And indeed, the answer is false. So very, very well done. We just talked about if you were adding on variables, you're adding in new variables that are combinations of the old variables. Maybe you don't want to add in too many. And if somebody already added some, it's the same thing. Like if you have variables that are there but don't reflect a pattern in reality, or you will overfit to those variables. So it's false, and the reason is because of overfitting. That's exactly what we just saw. Okay, what about the second one? True or false? Suppose x is one-dimensional. Is it better to use higher polynomials? So when you use higher polynomials, that would make it better, right? What did people say? And in this one, again, not quite as extreme, but 19 out of 24 people selected false, and the correct answer is false again. Why is the correct answer false? It's actually the same exact thing as the one before, which is you can think of x squared, x cubed as new variables, right? So you have the x, then you have the x squared, then you have the x cubed. They are all new variables, new features that you're doing, and more is not always better. And why is more not always better? Again, because of overfitting. So this one is false, and the reason is because of overfitting, just like that one. Okay, what about the third one? False, false, and is it always better to have a higher r squared value? Okay, surely this one. And again, you guys are too good for my tricks. This one is also false. False, false, false. And then the reason is because r squared always refers to, or when you run it, unless you are careful, r squared almost always refers to the training r squared, or the training error. So when running a regression, is it always better to have a better training error? And the answer is false, because of overfitting. So all three of these, the answer is false because of overfitting. And in the last one in particular, is mixing up the train and the test error. It's always better to have a lower test error or a higher r squared test value. But the default r squared is the training, and you don't always want to make that as high as you can because of overfitting. Okay, so these are 3 examples, and I'm going to show you details of each of them. I think we're going to start with this one-dimensional polynomial one and show you exactly how that would look. And that is this little thing, choosing the best polynomial power. And again, this is in the course GitHub, and it is using this this data set, which they also use in the book on cars, so autos. So this is cars, and this is horsepower versus miles per gallon, and every single dot is a different car. So we want to be able to predict which cars have good miles per gallon and which cars don't have good miles per gallon. Of course, miles per gallon you want to be as high as possible. And so it's maybe not surprising that the cars that are extremely powerful, like motor cars that are like, you know, a dragster, is not very fuel efficient, whereas a lower one is more fuel efficient. But there are, of course, all sorts of other confounding things, like what year was it made and so on. In this one, we're doing the one-dimensional version. So just horsepower versus miles per gallon. Can you find the best fit? And you can probably just see by looking at it, a line is pretty good, but not perfect. You can do better than a line. And that's exactly what we tried. So I added these polynomial features. And then I said, I did these different data sets. So I had horsepower, and I had horsepower underscore 2, horsepower underscore 3, horsepower underscore 4, and horsepower underscore 5. Those are the square, the cube, the 4th power, and the 5th power of the horsepower. So I added these features in, and I did it. I thought I had a thing that was like, just do it. But maybe I did it all with lists. Well, okay, I did it all with lists, and then I made these nice plots. So let's look at the nice plots. And here I was very careful to do the test and the train errors as 2 separate things. So the red dots are my test set of my predictions. The green dots are my training set predictions. And I've told you what the errors are, and they're pretty similar, 23 and 25. One thing I did that I could have done better is I did the mean squared error. I should have done the root mean squared error, because then I can think of how far away things are. Like this looks to me, you're like about that far, which is about 5. So you should be about 5 away on average. That seems like roughly correct. And these numbers are like 25, and that's because I have to take the square root for it to make sense. So that's a good like sanity check. Like if you're predicting the prices of houses and you're off by 7, you're probably not going to be that accurate. You should be off by like, you know, tens of thousands or something. So it's good to know what the orders of magnitude are. But the interesting thing is to add powers. So this is adding it as a quadratic equation, and you can see in this one the train error went down by a lot. So the train error went down to 16. The test error is down to 22. And again, just like eyeballing it, you're not that close. So the 16, to me, this is already maybe starting to overfit a little bit. But the test error did go down, and we do care about the smallest test error. So it went down from 25 to 22, so that's nice. And if you keep going, you add a 3rd power, not much changes, and a 4th power, and a 5th power. Then you start to get this, with the 5th power, you start to get this like little dip at the end, and it's even starting to go up right at the end. And that is in the train set. So the green is the train set. And so to me, this is really starting to look visually like overfitting. We're getting pulled away, these like weird patterns that don't fit everything else. We're getting pulled away by just a few points over there. And that does make sense because these values have a really high 5th exponent. 225 to the power 5 is much larger than 100 to the power 5. So these points over here are really large and are kind of pulling the 5th exponent. And you can see that the test error and the train error are getting further and further apart. So our train error keeps going down, and our test error is not really going down. And that's showing us that we're starting to overfit. We can plot all this on a nice little plot over here. So again, you can read the code, some nice little loops. You can see it looks like this. So this is the mean squared error as a function of the polynomial power. And as you add in more and more, the training error keeps going down. It'll keep going down forever. The more powers you add, the training error always gets better and better. But the test error was actually the best at 2. And that's starting to go up. So this over here is a kind of a crappy version of the U-shaped curve we talked about in the first few weeks of class. And if you were doing this as a project, you would say, hey, I should do maybe a quadratic is probably the best, but don't go past a quadratic. Okay. Any questions or comments about that so far? I have a couple other things to say about this one as an example, but it really is just, this is like the simplest example of the kind of thing you'll be doing on your project. You have a data set, you're going to figure out what features to include or not include. The way you're going to make decisions is by doing the train set versus the test set. You're going to talk about overfitting and underfitting, and you're going to pick the best balance, which in this case is a polynomial power of 2. Questions or comments? And again, they do this in the textbook as well. Yeah?
Is this based on like
Yeah, so it's on the course GitHub. So if you go to the course GitHub, and you go to the variable selection folder, and this is the one of choosing the best polynomial power. Yeah. Yes, very, very good question. Yeah, and again, this kind of goes with, they talk about this one in the textbook as well, so you can also check it out over there. Okay, choosing the best polynomial power. I will say, okay, maybe I'll give you one more fun tip. So if you click into it on GitHub, this will take you to the GitHub page, and then there should be a link to the top here, open in Colab, and then you can really run it and do everything. And you sign in with your Google account, you can make your own copy and play with it however you want. Okay. Okay, so what else can you do? So here I did the classical train test split that we talked about, and I think I did 20% of the data in one, 80% in the other. So I had this slice data function. Let me see. Was there something I had? Yeah, this is ordinary validation is the kind of thing we've been talking about. Let me see. Where did I take the train data? Oh yeah, I have xtrain and xtest. Okay, where were xtrain and xtest made? Let's find xtrain and xtest. Because there is a function for this that is quite useful that I think is worth showing. Autos. X, Y is this. Okay, here it is. Yeah, it's the function called train test split. So this is the simplest possible way to split your data, and it's automatically done in this scikit-learn framework. And what it does is it divides the training set. It divides your set into a train set and a test set randomly, and you can decide how big to make it. Here I made it quite large to really check on that overfitting. Does anyone know the disadvantage of making your test set very big? You need a test set big, you have a really accurate estimate of your error. What's the problem with a large test set? Yeah, it makes the training set smaller. So if you're making you're kind of sacrificing your training set for a test set, and if you do too much of it, then you won't have as good of a final result. So that can be a problem, but for this kind of thing, 0.5 is good. 0.2 is also very standard. Nobody will criticize you if you do 0.2, 1/5. So that's the sort of simplest possible way to split into train and test. And then there's fancier ways. So they talk about these in the textbook. One way is cross-validation and leave one out cross-validation. In leave one out cross-validation, you use this leave one out function. And what it does is it makes many data sets where there's exactly 1 point in each test set. So you do the whole training set except for this 1 point as the test set. You do the whole training set except for this other point as a test set. And then you do the regression. You sort of figure out this leave one out cross-validation. And then, so this is a very large training set. The training set is as large as it can possibly be, everything except for 1 point for the test set. And then you just loop over all the different test points. So this is see this loop over here is looping through all the different test points. And then you take the average of all these things, and you can see the average error was 24, which is quite high. So that's one way to do it, this leave one out. So the main disadvantage of leave one out is very accurate, but it's quite slow because you have to rerun the model for every single point. A kind of a compromise between the regular way and the leave one out cross-validation is ordinary cross-validation. Okay, what do I do? This so-called k-fold cross-validation. So there's this function called k-fold, and what it does is it splits up your data set into some number of pieces. Here I did n splits equals 10, so it splits my data set into 10 pieces, and then it uses each piece as a different test set. And here's the loop, looping over everything, doing the stuff. And you can see I ran it a bunch of times. I guess I only ran it 5 times here. LM5. Yeah, okay. And so you can get a more accurate estimate for the test error by averaging that way. I think they talked about these in the videos, but I haven't done it in class yet. So let me draw a little thing here. So this is ways to improve the ordinary train test split. Improvements to train test split. And so this is cross-validation. So here is your entire data set. And we split it into some number of pieces, very commonly 5 pieces. What would that look like? Like this. So, and then we say, use one, take turns using one piece as test and the other pieces as train. Okay, so you split the data set into 5, and you say like, I'm going to use this one as my test set, and then I will use the other ones as my training set. So maybe this one, these ones are all training. And then I do my error that way, and then I shuffle around which one's the test set. So I do the training, this one, and then I do it again with this one as the test set, and so on. So repeat number of times. Repeat for each piece, and average. Okay. And again, this is like somewhat tedious to do by hand, but if you use these like built-in functions, which is the main reason I'm telling you about it right now, if you use these built-in functions like kfold, then it can be a little bit easier. This is not required, but can be a nice small improvement you can do sort of without too much extra work. Okay, I think they talked about that in the video, so I won't go into more detail than that. The kfold cross-validation. Any questions or comments about kfold cross-validation? Okay, so this was a one-dimensional data set, right? We were only doing the polynomial power. Like we only had one variable, and we made more inputs by taking powers of this. But in your actual data set, it's very high dimensional, and that is where you can do this subset selection, best subset selection, which was also a topic of the videos. So that'll be the next thing. In high dimensional data sets, use best subset selection. Or maybe I'll get rid of the word best. And the reason I'll get rid of the word best is there's too many possible subsets to check all of them. And so you should not expect to be able to find the best possible subset. That would be too computationally hard because there's like exponentially many possible subsets. But in the textbook, they talked about forward or backward. And forward and backward subset selection is merely quadratic in the number of variables, and so is feasible to do on your computer. And I'm going to show you an example of that now. And once again, this is in the textbook as well. That is subset selection. Let me just check one thing in my notes if there was something else I was supposed to do first. No, okay, great. So best subset selection, and I did this on the hitters database. So this is a data set also from the textbook of different baseball players. And here's some information about the baseball players. The at-bats, the hits, the home runs, the runs. This is how good they are at baseball, right? Like, did they get a lot of home runs or not? Things like that. There's also a couple interesting ones over here that look like they're zeros and ones. What are these zeros and ones? Does anyone want to take a guess at what those zeros and ones mean? Yeah.
Categorical variable.
That's right. So these are just like the variable we saw before with the group. Either you're in group 0 or in group 1. These are different groups of people. And in particular, league and division are telling you which team they're sort of on. Are they in the East Division or the West Division? Are they in the AL League or the GL League? So these are different like groups of baseball teams, and this tells you which ones they're in. Okay? Okay. So those are some categorical ones that are already baked in as zeros and ones. So I've made the whole thing numbers just for the sake of argument. And what are we going to try to predict in this data set? We're going to try to predict their salary. So we input sort of each player individually, and we output how much money they're making. You might say, hey, these people are making very little money, $475. That's not very much at all. But this is like hundreds of thousands of dollars. So these people are actually quite well off. They're making a lot of money. And our job is to use all these different things to predict their salary. Okay. So what was the first thing I did? I implemented did I do forward or backwards? Let's see. Forward. So I implemented the forward selection algorithm, and here's the output. Let me remind you what the forward selection is. This was in the video that you saw, and that is the first kind of standard way to do it. So forward selection, forward selection. So start with no variables. Then we try all remaining variables one by one. So in other words, our model has many, many different variables, right? It has like 20-something different variables that we could possibly use. And to start with, I'm going to do none of them. And I'm just going to add them in one at a time. So I'm going to say, how well would at-bats predict their salary? Okay, forget about at-bats. How well would hits predict their salary? Okay, forget about hits. How well would home runs predict their salary? And I find the variable out of all of these, the single variable that is the most predictive of their salary, right? So I try them all and find the best one. Try all remaining ones. Choose the best one. The best one. Okay, and then we add this to our current collection of variables. Add this to our current collection of variables. And then we go to this step. Go to this step. So in other words, once we've decided who is the best, so let's see who was the actual best. So I tried them all. So I have this function called process subset and forward, which is running it. So process subset tries one thing at a time, and forward is doing this loop of goes through the remaining predictors. It's that step of add to the list of things, add on, trying that predictor. So the predictors plus the P, the new one. You can read the code details if you want, but it's doing what I just said on the board. And it turns out the very first thing, the best possible thing, oh, actually I tried them all. Okay, great. So I have this nice little loop that is printing out everything. So I tried just at-bats, then I tried just hits, then I just tried home runs, and so on, like I described. And I got all the way down to new league. And I told you the root mean squared error for each of these. So if you're trying to predict their salary based on only the number of times they were at-bat, there's an error of 410. If you're trying to predict their salary based on the number of hits they got, the error is 393. So how often you hit the ball is more predictive than how often you tried to hit the ball. That kind of makes sense. People who hit the ball more are good. People who get a lot of home runs, that was not predictive of their salary. And it could be because there's other, hitting home runs is more noisy, so it maybe makes more sense that something like the number of hits is more predictive. But which one of these individually was the most predictive? Let's see, 393, can we beat 393? 377. I don't know what a C at-bat is. Does anyone do baseball? What is a C at-bat? You have to go read the data set. Maybe it must be some special kind of at-bat. I wonder what C could be. Okay, I don't know. If you want to. Yeah, maybe something like that. It's some kind of special at-bat. I don't know what it is. You have to read the data set description to see. And I will tell you, like in your project, it's housing. You guys live in houses. You know what a house is. So reading what these things mean could actually be helpful for you, because it could be like, oh, just delete that. That doesn't actually matter, right? But in this case, it seems like the C at-bats, 377. Can we beat 377? Oh, the C runs. Okay, that makes sense. C runs. Anything else? Some of these things are very not predictive, like the errors or the assists. These have really high error. But the one that has the lowest error, I think, is the C runs, unless I'm missing one. Anyone see a lower one than 372? Okay, so what did we do? So we tried all of them one by one. We tried all the variables one by one because we started with nothing, so the remaining variables was all of them. We choose the best one, that's the C runs, and we're going to add C runs to our collection, and then we're going to go over here and try everything else again. So that is the next thing in the thing. So we added C runs to our thing, and now we're trying everything else with C runs. So you see C runs on its own, where was C runs? Had an error of 372. But if you do C runs with at-bats, you get an error of only 330, right? So if you use two things to predict, the error goes down. And you can get all of these different things. And you can see which pair that includes C runs is the best. And it looks like C runs plus putouts has a very low error of only 305. That's very interesting. Putouts on its own was not very predictive, right? Putouts had a huge, look at this. Putouts on its own had a huge error, 467. But in the presence of C runs, putouts is very helpful. And so that must mean that like putouts and runs are kind of measuring two different things. And if you know about somebody's runs, then it would be helpful to also know about their putouts. I'll tell you, I know very little about baseball. I already have a theory of why putouts is helpful with C runs, even knowing kind of almost nothing about baseball. Does anyone have a guess why these two things would maybe go kind of opposite each other in a way that knowing both would be helpful and knowing one on its own is less helpful? Yeah?
One is defensive and the other is offensive?
Yes, exactly. So C runs is like how good are you at scoring goals, And putouts is like how good are you at taking the other team out, so defending. And so it kind of makes sense that if you already know somebody's C runs, then knowing their C home runs won't help you like learn more about them. Like we already know if they're good or bad at that. But knowing their putouts will tell us, hey, actually this person, maybe they're not very good at runs, but they are good at defense. So it kind of makes sense that things that are telling you different aspects will have a lower error together than things that are telling you the same thing. And you'll see that in your housing data set, right? So maybe there's like one is like neighborhood and one is like size, and different neighborhoods have different prices, and within a neighborhood, size could mean something different, right? So what you do in combination with other things, like there's an interaction between them. Okay, so we're gonna add putouts to our thing. Can anyone spot a number lower than putouts? Of course, the computer will take the minimum for me, but this is sort of fun to look at it by hand. So very good. Okay, so we'll go back. We're gonna add putouts. Now our set contains C runs and putouts. We go back to this step, and we try all the variables again with those two things. Okay, and what does it look like? So now we got C runs, putouts, and at-bats, blah, blah, blah. We try all of them, and I don't know, what's the best one now? 306, something like that. Okay, anyway, we try all of them. We keep doing this until we've added everything in. So by the end, we have, if we scroll down more and more and more, we will have there's only two things that are missing. Look, home runs got added in right at the end, and then C at-bats. But by the end of it, we've run them all, and we have all of the different models. One thing you might notice, the RMSE here at the end, I've added in all these variables, and the RMSE went up. So before I was doing just two variables, it was like 300. Now it's 330. What is up with that? Anyone have a guess of why the RMSE went up when I added more things it could predict with, and the RMSE went up? Sorry? I'm overfitting. Yes, that's right. So I'm overfitting, and this RMSE, look, I did exactly the thing I told you guys not to do, which I didn't tell you what type of RMSE this is. This, for sure, is the test RMSE. We can check the code.
So it makes it worse.
So it makes it worse. Adding in more things makes it worse because of overfitting. And let's see. So I have the RMSE of the models. What is the RMSE of the models? Round models RMSE. Oh, probably in process subset it makes the RMSE. I want to make sure it's the test set. Okay, look at this line. RMSE equals blah, 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 square root of the mean, but X test. So this really is the test RMSE. And if I was smarter, I would have written test, right? Because now I have to go debug and find my code. Is the RMSE the test or the train? And now we know it's the test. And so life is good. This is the actual number we care about. And so it goes down for a while, and then it starts to go up. And we can have a nice plot of how it works. So these are all the different models we came up with. And here is a plot of the RMSE. I should have written test RMSE, but I was lazy, and that is bad. The RMSE, the test RMSE versus the number of predictors in our little loop. And you can see it goes down for a while. So one predictor on its own, not very good. Two predictors, pretty good. Improving a lot. By the time you get to 10 predictors, it has improved a little bit more, but then it starts to overfit. And you can clearly see the overfitting. This is the clear overfitting phase, where adding in more predictors is making the test error worse because we are chasing down patterns in the training data that do not exist in real life. Okay? And so this is the forward subset selection. The one in red is the absolute minimum. I would make a good argument that if it's about equal, you want to pick the one that is smaller. So I would probably do 8 here. That's because the more you have, the more chance you have of overfitting. So there's a small jiggle in the errors here. The 8 would be the lowest one that is kind of about the same error. So I would use 8 or 10, and that is the forward selection algorithm is choosing a subset, exactly what we described, choose the one that has the lowest at the end. Okay, so that's like the last step over here. So once finished, choose the number of variables. The number of variables that had the lowest what? And this is very important, you fill in the blank here. The lowest RMSE, which kind of RMSE? The lowest test RMSE. If you pick the lowest training RMSE, this will absolutely blow up in your face because you will just pick the one with the most variables, so that's not good. Okay, the lowest test RMSE. Okay, so we say, hey, look, the best thing we can do for predicting the salary is to use 8 or 10 predictors, something like that. That is the best you can do. Okay, and so you come up with this model, and here is the model. So this one tells you all the different variables that were used and what its RMSE was. So C runs, put out, C walks, runs, C RBI, what league you were in, things like that. And you get an RMSE of 287.75, 288 or 287, depending on which one you want to use. That is the best model we can think of using the forward selection. Okay, and I will tell you, this algorithm is a perfectly valid way to do your project. So if you want to do your project sort of in a straightforward, simple way, you're gonna have to do some data cleaning and like some manipulation stuff. We'll talk about that a little bit more. But this is like, this could be the heart of your project, is I'm just gonna use forward selection to find the best selection of variables I'm gonna use, and I'm gonna make sure that I don't overfit because I'm doing this thing, and I have a U-shaped curve in the number of variables. So this maybe I'll add this. This makes a U-shaped curve. This makes a U-shaped curve in test error versus number of variables. And then you can talk about that for over and underfitting. Okay, so perfectly good way to do it. Any questions or comments about the algorithm or how I ran it on this thing? So this is all using the scikit-learn framework. Okay, so what else can you do here? So first of all, this is kind of like scratch work. You gotta clean it up a little bit. What else do I have here? What happens if you, this next thing, this is to warn you what kind of traps you can fall into. So here is, you could rerun all the same code, and if you get a plot like this is a common mistake. I think I've jumped up and down about this mistake many times now. If your plot looks like this, then you're plotting the training RMSE and not the test RMSE. And you're thinking, oh, it gets better. Every time I add more variables, it's getting better and better. You will not realize you're overfitting unless you look at the test RMSE. So that's an important distinction. I think maybe when I had this originally set up, the reason, maybe I left this out on purpose so that I could then bring it up here. Okay, I guess I spoiled it by calling myself an idiot. Okay, that's fine. Let's continue. Okay, there is one last thing you can do to improve your model. So this is very good. This is not good to use the training set. But there is one advantage to the thing in brackets here of no test set. So this is a last step to squeeze out just a little bit of extra performance. So up until now, I've been running this training set and this test set. But there is one thing you can do with no training set. What to do with no test set. Okay, so up until now, we've had this starting at the top here and up until this line. It's really important we've had the test set so we can compute the test error. But now I'm telling you, there is one last secret step that you can do with no test set. No test set at all, only the training set. What would you do with only the training set? So what is this step and what are we gonna do? Anyone have a guess what is gonna go on here? Yeah. Yeah, that's right. So the no test set is a very pessimistic way of putting it. I'm saying the cup is empty. You should think of the cup as being full of the other stuff. So no test set means use the entire training set. Okay. So up until now, we've been using the test set to make decisions like how many variables we're going to use. And when you're done, once you have made your decisions, you should rerun everything. Now that you've made your decisions, rerun everything using the entire train set. So I'll write that down. This is an important last step that people often forget. Okay, so once you are finished, oh, I don't want this one. Okay. Once you have finished making choices, and we gave a name to these things, we called them hyperparameters. So I will call them hyperparameters. Once you have finished choosing hyperparameters, okay, and in this problem, the way we set it up, there is one hyperparameter, which is the number of variables, right? E.g. So in this forward selection, the hyperparameter is the number of variables to use, and this algorithm runs through and it finds which hyperparameter is the best based on the train set. And so this is the last little principle. Once you have finished choosing your hyperparameters, you should rerun everything on the entire training set. Then rerun on entire train set. So in other words, your best possible thing isn't what you discovered up here. All this procedure up here was just to figure out the best value for your hyperparameters, and then you should rerun everything using the hyperparameters that you found. And the reason is, that way you can use a slightly larger set. So this set is smaller because we held out some for the test set. This set will be slightly bigger, slightly more data, and so you should have slightly better performance. And this matters when you submit on the leaderboard, you will submit this thing. This is the thing we actually want at the end of the day. So this is a step people often forget, so it's worth writing down in all capital letters so you don't forget it. Questions or comments about this one? Yeah?
So if you run it on the entire train, like in the beginning when you have the whole set, you might
Right.
to write the training set and the test set.
That's right, yeah.
So if you're saying we should rerun it, you said with the overfitting error.
Yeah.
With the training set.
Yeah.
So now that training set is contained.
Yes.
This new
Yes.
training set, so
This is exactly right. Okay, so this is important. This is what I mean by rerun. The rerun is doing some heavy lifting. And so rerun means rerun it. Let's put a star equals with the hyperparameters you found already. With the hyperparameters you found already. Okay, so what I mean is, when I say rerun it, I don't mean throw everything away and start over like you've done nothing. I mean, using the best variables you found in the first step, take those choices and apply them to the entire data set. So let me give you a very specific example, right? So in the model over here, we did all of this running, and then we generated this nice table of here's our best model with one input. Here's our best model with 2 variables, 3 variables, 4 variables, and so on. And then we said the best model is the one with 10. This was the best one. So when I say rerun it, I don't mean start over as if you've done nothing. I mean take this line, your 10 variables, and apply the 10 variable situation to the entire set, right? So this model right now was generated from the training set, which is 80% of the data. Take just this line, which is your best hyperparameter, and apply that to the entire set. And you'll get something slightly different. Why will you get something slightly different? Because remember, this is a linear regression model, and it has parameters, right? It has slopes. And if you rerun it on the entire training set, the slopes will change a little bit because of the extra data that you've injected, and you'll get a slightly better model with slightly more data. Okay, there is one important issue, which is which of these are we going to rerun? Are we going to rerun a model that includes exactly these variables, or are we going to run a model that has 10 variables? And you could do either one, but it is better in general to do just the 10. So say the hyperparameter that we're doing is the number of variables. Let's do it again with 10 variables. And that is what I did at the very end over here. So to show you for added clarity, here is the thing. So even though the training RMSE is going down, down, down forever, I know from what I did before that actually I should stop at 10. So 10 is where I'm stopping. And here is the predictor with the best 10 variables. So, and it turns out they're slightly different than what they were before. So let me show you this last line. The best 10 variables we found from the training test split was this. And the best 10 variables from the entire model with no test set is a slightly different 10 variables. And the 10 is the thing that we were doing. We were working really hard to find the 10. Once we know the 10, those are the 10 we should use. And they're slightly different. And you should use the one on this one. That'll be slightly better than the other one. So that is the moral of the story here on this last little step for squeezing out a little bit more data. This whole game with test set is just to make decisions. Once you have made the decisions, you should rerun on the full set. Okay. Very good. Other questions or comments about this? Yeah.
Why the variables different since you already know the entire data set because
Yeah.
it's divided into 2, right? Training and test. So the model is already aware of the 10 best. So how do they differ when
Yeah. Okay, this is great. So okay. there's maybe one confusion. So in this data set, there's one data set, and I split it up into the training and the test. When you guys do your project, there's two data sets, right? There's the thing I gave you, and then the one that I'm holding for the leaderboard. But when you are making choices, you're going to take the training set, and you're going to split that further into pieces so that you can make decisions. When you run the regression, so when it ran, okay, let's find where it was. When it was doing these runs, right? The error it reports. So for example, when it ran at bat, option 0, it tried the model just at bat. This is the test RMSE using the model that was trained on the training data points with at bat. If you train it with a different data set, you should expect these things to be different, right? And so in this one, what did we say was the best? C runs was the best, right? So C runs was the best. But if it was on a different data set, maybe C hits is the best, right? So what is being done depends on the training set, and then the error you're predicting depends on the test set. So if you change either of those, things will change. Yeah. Okay. Yeah.
So you're saying the number 10 is the important part of this?
The number 10.
The actual selected parameters?
That's right. Yeah. Yes. They have one of the videos. They specifically talk about this. I think it is a pretty subtle difference. So I think if you did the 10 best variables you found, you would get pretty close. You would be like almost as good. Yeah. And the reason is, again, it's overfitting. You're sort of like overfitting to which parameters were important for predicting on the specific set you had. So you'll generalize slightly better by keeping the number 10 and not keeping the variables. Yeah, so if you're into this stuff, again, this is like statistician stuff, and those guys will explain it better than I will. Yeah. Okay, yeah, great question. Anyone else? Yeah.
So when you said we run everything on the entire training sets,
Yeah, that's at the.
you mean we should do the subset selection again?
Yes, you have to run it again, and that's what I did here, right? So I ran the subset selection again, and I was using the training RMSE to make every choice. And this seems to go down forever, but I'm saying stop at 10. So run it until you're at 10 variables. And the reason it's 10 is because I figured out 10 was the right answer from before. Yeah. That's right.
Would be your best variables then?
Yeah, the best 10 variables are these ones. They're the ones that came out when I ran it. So I ran it over here, and then I guess, okay, if you want, show hidden output. This will probably print it. Yeah, this is the run with doing it. So the RMSE here means the training RMSE, and it's fine. We're doing it forever, but you should stop at 10. Yeah. Yeah, that's right. So this is like a last secret step that people miss, is that you should redo everything once you have. So you have sort of two phases: choosing the best hyperparameters, and then once you've chosen them, you should do everything with the best hyperparameters you found. Okay. All right, let's move on to another very practical issue. Let me see what it is. Okay, yeah, great. So again, another practical issue you will have. Let's skip this one for now. Let's do this one. Okay, and we talked a little bit about this at the beginning of the class. Is what do you do with categorical variables? So far we've talked about the group 0, group 1. We saw how that worked. And then in the hitters data set with the baseball people, there was the leagues, and that was sort of done for us. But in your actual data set, you're going to have to decide how do you convert things that are given to you as categories, how do you convert them into numbers? Because numbers are what have to go into linear regression. Linear regression works by multiplying by a slope. You cannot multiply red by a slope. You can multiply a number by a slope. And so here is an example. You have red, green, and blue, and here are 3 different ways you can put it into your linear regression model, either as what is so-called ordinal encoding, so you assign the numbers 1, 2, 3 to red, green, and blue, or one-hot encoding, where you make columns. You make a column for are you red, are you blue, or are you green, and red is a 1 in the column are you red, and 0 in the others, and so on. And then there's also this option called a drop first. And in a drop first, you take the one-hot encoding with 3 columns, and you delete one of them. So you get red 1, 0, blue is 0, 1, and green is 0, 0. And you're supposed to know that if there's 0 in both, then it must be green, right? So those are the 3 options. And the question is, you want to put this in a linear regression model to convert it into numbers. What is the best way to do it? And this will sort of lead us into a discussion on what are some pros and cons of these different ways and things like that. Okay, I'll give you 1 minute to try that. All right, 30 seconds left to take your guess. I guess I made this an all that applies. So you can pick more than one if you want. All right, let's see what people said. People said, drum roll. Okay, so out of 24 people, 6 people said ordinal encoding, 8 people said one hot encoding with 3 new columns, and 15 people said one hot encoding with 1 less column. So this one's the most common one. So I'm going to tell you there's potential issues with the ordinal encoding that has some issues, and there's also issues with the option number 3. I will talk about them in 1 second. But the biggest issue is the ordinal encoding. So this is, I think, the most common error people have made in previous years on the project one is they took things that should not be ordinal encoded and they used ordinal encoding. So let me tell you what is the problem with ordinal encoding. So this is a kind of a practical little tip over here. What is the problem with ordinal encoding? Okay, what is the problem with ordinal encoding? And to remind you, so we have red, green, or blue. Red, green, not greed, that's something else. Okay, blue. And that gets mapped to some number. I'm going to call this X color, where X color is either 1, 2, or 3. X color is either 1, 2, or 3. So, it's a very nice way you can recover the information of are you red, are you green, or are you blue. So for some methods, it works perfectly fine. But for linear regression specifically, this is setting up a little hidden problem that is scary. Okay, so you're going to have beta hat color times X color. And that's going to be in your regression, not X hat color. Okay, X color plus dot, dot, dot. So you're going to have Y equals this stuff. So we converted red, green, or blue to the number 1, 2, or 3. Then in linear regression, you find the right coefficient and you multiply it by X color, and that is it. So that's what we've done so far. So why is it a problem? Who can tell me why this is a problem? Yeah.
Unless there actually is an effect where somehow you've guessed an order right, you are converting information into noise.
Yes, that's right. So I think I like the way you said the order. So look, I went red, green, and blue, and I changed that to 1, 2, and 3. And there's no reason it had to be red, green, and blue. It could have been blue, red, then green, right? And by changing it to 1, 2, and 3, and then multiplying it by a number, I have implicitly said that blue is 3 times bigger than red. So this is the assumption that I have made. Sort of, it doesn't look like I made this assumption, but by the sequence of logical steps that I've done, I have done it without saying, which is I have chosen blue is 3 times larger, is 3x bigger than red. So whatever effect red has on our y value, blue will have a 3 times that effect, and it's because X color is 3 times bigger for blue things than red things. And so unless this assumption is justified by what you're doing, like if you know for a fact that blue is 3 times bigger than red, then this would be true. But other than that, you do not want to make this assumption. This will really screw up your use of the information. And the model is going to try to find the best value that works with this assumption, which is very far away from having a good prediction. Okay? So when you do ordinal encoding on things that are not in order, you have this big problem, and it's really going to screw up your use of this data. So be very, very, very careful with ordinal encoding. Let me give a very specific example. Your data set, the housing data set, has something called quality. In the housing data set, there is a category called quality. There is, I think it's like quality. And the way the quality data set works, or the quality column, is some like real estate agent went to the house and was like, this house is a 7, okay? So it's a 1 to 10 of the quality of the house. Like, is this house falling apart? Is it like really well maintained? And it's 1 to 10. Is quality an ordinal? Okay to put as ordinal encoding. So it's like 1 star, 2 star, 3 star, 4 star, and 5 star. And a lot of people, I think their first instinct is, yeah, like 7 stars is twice as many as 3.5 stars. So if the real estate agent says it's 7, it should be twice as many as 3.5. I should have picked an even number. If the real estate agent says it's an 8, that's twice as many as a 4. Like, that seems reasonable. But again, the thing is, we want to predict the price, right? And so by saying, I would say the answer is no. I would say no. And I would say a house that is an 8. Again, we're not talking about the total price of the house. That would be completely crazy. But even the effect of an 8 versus the effect of a 4, I don't think it's necessarily double the effect. So it could be that like 1 to 5 stars are all crappy. They all have kind of flat. And then it's like, okay, once your house is like a 7 or an 8, then the price goes up, right? And by using ordinal encoding, even for this thing called quality, you will have this assumption baked in that whatever you do for an 8 has to be twice as much as what you do for a 4, and you don't necessarily want to do that. Is not, I'm going to say necessarily, twice the effect of a 4. Okay, that being said, I would say maybe no. So you could experiment with the data and see like, is a linear thing actually good? Is an ordinal encoding actually like matching well? So the ordinal encoding, it has this built-in assumption, and you sort of have to check and verify, is it justified or not? And it could be, it might not be, it depends on the situation. And that's one of the things you have to do in your housing data set, is something like quality, you should investigate and see, does it make sense to do an ordinal encoding? Could you try to figure out, like, is it linear or not? Maybe there's some way, maybe if you take away everything that's less than 3, then it's linear or something, you know? So this is like the kind of issue you should investigate and think about when you are converting the raw data set into something you're going to use in your regression. This is the kind of thing you should think about. Okay, that's it for ordinal encoding. We're going to talk about one-hot in a second. But so any questions or comments about this ordinal thing? The moral of the story is, if you're doing ordinal encoding in linear regression, you should be really, really, really careful, because linear regression just multiplies the numbers, but you like don't see this equation when you're working in the code, and so it's easy to forget that's what you're doing. Okay, the other type is one-hot encoding, and one-hot encoding also has some issues. And in particular, I'm going to talk about what is the issue with drop 1, or what is it called? Is that what I said it's called? A drop first equals true with drop first equals true. Okay, and I will tell you, there is a mathematical equivalence between drop first and not if you include all the variables. So let's say it this way. If x blue plus x green plus x red equals 1, then the two models with or without are equivalent. The two models are equivalent. And the two models I'm talking about are y hat is beta hat 0 plus beta hat blue x blue plus beta hat red x red plus beta hat green x green. Okay, and that's one model, model 1. And the other model is dropping one of them. I think I said I dropped green, so let's drop green again. So x blue plus beta hat red times x red. So if you leave out the green, the fact that they always sum to 1 means that the sum of blue, red, and green can get absorbed into the beta hat 0. So model 1 and model 2 are equivalent. Model 2. So you set beta hat 0 of model 1. That equals beta hat 0 of model 2. And then something plus something like the average, or the sum beta hat blue. I will leave it as an exercise to you to figure out the details. But because they always sum to 1, you always have this sum going on, and you can sort of absorb that sum into the intercept. So this is why people say, oh, it's like good, like just leave it, you'll have less variables to work with. But there is one issue. There is one issue. And it's kind of a more subtle thing. As long as you do this exact model, everything is fine. But as soon as you start tinkering with the model, it will no longer be equivalent. And for example, what were we just doing in this class several minutes ago? Apparently not going on here. We were doing things like subset selection, right? We were choosing subsets. And as soon as you choose subsets, if you delete, like if you take out blue or green, then the models are no longer equivalent. So with every single thing, they are equivalent. But for example, if x blue is deleted, they are not equivalent. Okay. So if you delete x blue, then model 1 and model 2 are no longer equivalent, and so maybe there is some reason you want to keep green. So if you're doing things like subset selection, then it's important you keep all the variables and do not do a drop first, because the equivalence kind of relies on every single thing being there. So if you want to do things where you're like playing with the individual variables, then I recommend you don't do a drop first. And it's really is because of this reason, not equivalent, so e.g. in subset selection, which we've been talking about. Okay, and that's the issue with the drop first. Even though if everything is there, they're equivalent. When you start dropping things, it's important you have the flexibility to include the green on its own. Okay, I think that's all I have time for today. I have a couple other little tips, but then we're going to start a new topic on classification quite soon. So it is not too early to start working on your project. Depending on how comfortable you are with this stuff, you might want to start with the tutorials, or you could start with the code, like the subset selection code that I had over here. You start with that, start playing around with the data and doing things. There's some things I haven't talked about much at all, which are like things like what to do if data is missing. I think you've been talking about that a bit in your other class as well. There are many different ways to handle that. Anything that is reasonable is fine. We'll talk a little bit about it next class. Any last second questions or comments before we adjourn till Wednesday? Okay, let's stop there, and we'll see everyone on Wednesday.